Right? So let's start with, so we are done with mathematics for now. Classical physics. So it all starts with Newton, right? Isaac Newton's Principia. Right? 1687. So we have laws of motion, right? What are the laws of motion? 1. No force, constant velocity. Right? No force, constant velocity. Second one, force is equal to change in the momentum. Or you can write it like this. And if m doesn't depend on time, provided that m doesn't depend on time, it's m times a. Right? If m depends on time, then you should really go with change in the momentum. Do you have any questions at this point? No. Third one, action equals to reaction. You all know this, so I'm just writing it down. So momentum is mass times velocity, and momentum will be crucial to our understanding of quantum mechanics. So just all these are reminders of classical physics. Let's talk about determinism. Okay, determinism, don't take this as a definition, okay? If I know interactions, positions, and momenta of all particles, okay, then I know the past and I know the future. That's what determinism tells you, right? You take a gas, let's say, or a human being composed of trillion, billion atoms, I don't know. You know all the positions and momenta. You know what he or she is going to do. That's determinism. What's going to happen? So, we are going to have problems with determinism, okay, in quantum mechanics. Let me remind you about potential energy. We will use potential energy. That's why I'm mentioning it. So it's energy due to relative positions. Energy due to relative positions. For example, let's say there are two carbon atoms. Okay, we put springs between them, but not necessarily. Just two carbon atoms. And this is the distance between them. Okay? If you plot the potential energy of this, you will get something like this. Right? This is R versus V of R. So, just to give you the how you should think about it, if the system is at this state, it's like a ball that wants to roll down to the minimum. If the system is over here, meaning that they got too close, then the system will go back here. Okay? That's what potential energy is. Do you have any questions at this point? So relative positions create energy, and that energy is minimized at a certain arrangement of positions. What is force? Force is the gradient of the potential minus negative gradient of the potential. What does negative gradient mean? It means negative del V over del X in the I direction, negative del V over del X, del Y, sorry, in J direction, del V over del Z in K direction. Okay? Any problem here? Very good point. Actually, you can define potential energy for conservative forces. If there is a non-conservative field, okay, then you cannot really define potential energy, because potential energy assumes that if you go around and come back, the energy will not change. But in a non-conservative field, it's not necessarily the case. Okay? Very good point, very deep point. So conservative. We are going to deal with conservative systems. Let's talk about work. What is work? Work is integral over a path dx. Like for example, I have a mass of m and I'm moving it with an acceleration a, let's say, over a distance x. What is the work done? Mass times acceleration, which is force, times x. That's the amount of work that is done on this object. Okay? What is kinetic energy? We are going to use all this, so just defining everything. Kinetic energy is, okay, let's write it. Work done to accelerate a body from rest to its current speed. All right? So we have just accelerated this body, right? How much kinetic energy do we have? Well, work done is m times a times x, right? And we also know that x is at squared over 2. Do you agree with this? Just linear acceleration, constant acceleration. And v is a times t. So let's put it together. ma times at squared over 2, which is ma squared t squared over 2, which is mv squared over 2. So we will show kinetic energy as k, maybe as t. So it depends on our mood. It's mv squared over 2. A more popular version of kinetic energy in this course will be p squared over 2m. Okay, we will enjoy working with momentum more than working with velocities. Okay? Do you see how it's p squared over 2m? Yes, because p is m times v, right? Now comes Hamiltonian. Okay, no, before Hamiltonian, let me just show you something. If you plot E versus P, and this will be a very important plot. Okay, we will keep plotting E versus P all the time. What do you get? A parabola. Okay, if you have a parabola in the E versus P graph, then it corresponds to a certain mass. Okay? And that mass is defined by the curvature of that parabola. If it's more up like this, then it's more mass or less mass? If you have higher curvature, less mass. Lower curvature, higher mass. Okay? Don't forget that. If there is no curvature, there is no mass. Okay? We will see E versus P's that look like this. Okay? There's no second derivative here. This is a behavior of, this is how light behaves, for example. E equals to P times C, and light doesn't have mass. We will see that in some materials, electrons behave like that, and we call those electrons massless Dirac fermions. Okay? Good? Yes? Total energy. Kinetic energy. Kinetic energy. Sorry, kinetic energy. Yes. All right. Let's talk about Hamiltonian. Anyone who knows what's the difference between Hamiltonian and total energy? Huh? Have you taken classical mechanics? Yes? Do you know?
It depends if you have time symmetry or not.
Right? So if you don't have time symmetry, which one is larger encompassing thing? Hamiltonian, right? In this course, Hamiltonian is total energy is Hamiltonian, okay? We have no such ambiguities in this course. We will just show Hamiltonian as kinetic energy plus potential energy. This will be total energy. Okay? Let me also write down Lagrangian. Okay, you might ask me or yourself, why do we define energy at all? Right? Why do we define momentum? Why we don't call something like mv cubed over 3 something and just go with it? Right? Do you have an answer to that? Do you understand my question? Defining energy, you get rid of vector calculation.
You kind of converting the vector Newtonian calculation to the energy.
I see. For example, how about conservation? Energy is conserved. That's why you are interested in that kind of quantity, isn't it? Momentum is conserved. You are interested in momentum, right? So we always have some reason, some physical reason to define these things. And Lagrangian is the trickiest one. It doesn't seem to have any physical significance, except that it appears in the deepest law of nature that we have. Okay? Lagrangian is kinetic energy minus the potential energy. Just take it or leave it, okay? Lagrangian is this. If you haven't taken classical mechanics course, you are seeing this for the first time. Are you seeing this for the first time? Because you took classical mechanics, right? Okay. Okay. Now comes one final thing that you probably don't know. Action. Okay, action is, action is the integral of Lagrangian over some time. And do I need to say also some path? Yes? What am I missing here? Anyways. Yes.
Why don't you write L dt?
Let me write L dt. Okay. I'm confusing myself right now with the path. Should I have the path variable here as well? My intention is not to derive this, so just hear the story, okay? Here's the deepest law of nature, principle of least action. Say it again. Are you ready to get the deepest law of nature? Yes? Deepest law of nature, let me just write it down. Because it works across the fields, like it works in classical mechanics, it works in quantum mechanics, and it works in gravitation, it works in standard model. In all this, we define an action, and then based on the principle of least action, we get the relevant equations. How did we arrive at this? We arrived at this by by thinking about Newton's equations in a more mathematical way, okay? Like one thing led to another, and we arrived at this principle of least action. So what does it mean? Let me tell you this. Let's say I have a system, and these are the coordinates of the system, x1, x2. Okay. And this x1 and x2 could be position and velocity, for example. Okay. So what do we know from Newtonian physics? We know this. Okay, let me just make it x1 and p1. If I know x1 and p1 in Newtonian physics, some of you are detached. This is very important. Now you listen, okay? Please. So if I know position and velocity in Newtonian physics, how does Newtonian physics approach it? It tells you what is going to be the position and velocity in the next time step. It's a local law, right? It tells you what's going to happen right next to that time, and right next to that time, right next to that time, right? And that's how you find that the particle will go from this point to this point. Okay? Newton's laws guide you over this path constantly. That's how Newton's laws work. Now, people started thinking about Newton's laws and discovered that, okay, let's go in this direction, let's go with this path, let's go with this path, let's go with that path. They are just changing the path. Okay. What happens is that if you calculate action for this one, action for this path, action for this path, action for that path, action for that path, the one that follows Newton's laws has least action. Did you get it? So Newton's law are telling you what's going to happen locally, right in the next moment, while principle of least action looks at it globally, taking into account all possible paths that a system can take, and the path that minimizes this action over here is the one that the system takes. Did you follow this? So, if you just find the path that minimizes the action, then you arrive at Euler-Lagrange equation. So Euler-Lagrange equation is derived by the following. You first start from this global view, and then you find the microscopic law that would make sure that the path taken is the one that gives us least action. And it turns out that the equation looks like this, like del L over del X. I'm simplifying things. dt del L over del V of X equals to 0. And this is true for each coordinate and for each particle. So the X coordinate of the first particle, then you will get this one. Do you understand? So each particle is following this. Okay, let's apply it to just single particle moving along. So what is the Lagrangian? Kinetic minus the potential. What is kinetic energy? mv squared over 2 minus the potential. So what is del L over del X? It's negative del V over del X. Don't worry, it will come back. What is d over dt del L over del Vx? It's d over dt mvx. So the Euler-Lagrange tells us that minus del v over del x minus d over dt mvx equals to 0. Then it tells you that f equals to dp over dt. You see, we have recovered Newton's law from principle of least action. Why I'm mentioning this to you? Because of what I'm about to mention next. That's one reason. The other reason is that Is it? Come on. I don't think it's before Newton, but can you check it? Okay, Euler is before Newton, but Lagrange is after. What? Yes, exactly. So you couldn't have calculus before Newton. Okay, figure it out. You were wrong. Okay. Couldn't be happier.
This is more general stuff.
Yes. Yes, you can derive everything from this. So there are two reasons. One is the next stuff that I'm going to tell you. And the other reason is that at some point I'm hoping to connect everything. Okay? One of the connections is that nanoscience, nanotechnology is supposedly started with Feynman. Okay, so he has this this lecture that he gave. There's plenty of room at the bottom, and people attribute nanoscience and nanotechnology beginning to that, which is not the case, but it is also sort of the case. Also, not Newton. Feynman's thesis is Lagrange formulation of quantum mechanics. So you see, it all connects somewhere. Yes, you have a question.
So we hope that the action function is very important. So how can we actually define or reach the action function? Is it right function?
Do you mean like?
So you define Lagrangian here, and you hope that this is the action function.
Do you think? Are you asking the physical significance of action?
Yeah, how can we define it? For example.
I mean, I don't have a handle on it myself, like personally. But since nature is insistent on minimizing it, it's like the amount of work that nature has to do, and assuming that nature is lazy, it always does the least amount of work. I see. I understand. Deep stuff. And whenever you start saying entropy is too deep. Let's move on. Sure.
We said that to the lowest path, we should minimize the action.
Mm-hmm.
So why don't we just simply take the derivative of action and equals it to the zero?
Okay, that's how you get. Very good. Very good. That's how you get Euler-Lagrange equation. Okay.
Okay.
Very good. But you are taking the derivative with respect to all possible paths. So there is some sort of a mathematics involved there. But it's nothing that you can't do. Okay. Noether's theorem. Yes, she should have gotten Nobel Prize for this. Every symmetry has a corresponding conservation law. And Noether's theorem, she derived this theorem from principle of least action. Okay? She realized that for each symmetry, for example, what is symmetry? Let's also define symmetry. Symmetry is operation that doesn't change action. Okay? Let me give you examples. So I will write here symmetry, and I will write here conservation law. Okay. Time. Your system could be symmetric in time. What does it mean? You have an experiment here at 1 a.m. Was 1 a.m. the good time? No, it's 1 p.m. Okay, 1 p.m. You don't do experiments at night. 1 p.m. you do an experiment. Then let's say, I'm just speaking, no worries. Let's say you repeat that at 1 a.m. Okay, and assume, okay, let's do it 1 p.m., 2 p.m. Nothing has changed, temperature was the same in the room, etc. You don't expect the system to behave differently. Okay? Assuming that your system is not time dependent, if your system is time independent, okay, then turns out after doing proper calculations, turns out energy is conserved. Okay, it's coming from this deep mathematical analysis of Noether. Okay, I'm not expecting you to see it right here because I didn't show it to you how we went from time to energy, but I'm telling you where it's coming from. If you because Noether's theorem involves some mathematics, and it shows you that you basically can use that mathematics to know what is conserved when something is preserved. Okay, some symmetry is there. So symmetry in time results in conservation law. Symmetry in translational symmetry, translational. Do you know what translational symmetry is? Should I just write space maybe instead of time, instead of translational? So symmetry in space. What does symmetry in space mean?
It implies two then.
What?
It implies two conservation laws.
Yes. So I do an experiment here, okay? Then I do the same experiment over here, okay? If it doesn't depend on that, if the system doesn't depend on that, then turns out momentum is conserved. I will show you a very good example of this, okay? And rotational symmetry results in conservation of angular momentum. These are the kinds of stuff that I ask in the exams, like fill in the blanks. Time is, we have symmetry in time, what is conserved, etc.
What about conservation of charge?
Okay, that's because of the gauge invariance, right? This started happening too often now, right? I will report it to the relevant people. All right. So let me give an example. This person has a ball and it's going to be thrown like this. So what is the Lagrangian of this system? mvx squared over 2 plus mvy squared over 2 plus, no, minus mgy? Minus mgy, because it's minus the potential energy. Do you agree? Does this have a symmetry in x? So remember, the symmetry in x is that if I change x coordinate, action doesn't change. If I change x coordinate, does it have a dependence on x coordinate? Not vx. Vx doesn't count. Vx is another coordinate. Does it depend on x? No. Does it depend on y? Yes. So there is no symmetry in y, but there is a symmetry in x. What we know from this motion, by the way, we know that Vx will stay the same. So symmetry in x results in mvx equals to constant. While no symmetry in y, momentum in y changes. Do you see it? We don't have symmetry in y because there's minus mgy. If I change y coordinate, potential energy will change, action will change. So action depends on y. So no conservation on y direction. Okay? If we are doing it on a flat plane where x and y does not enter as potential energy, then momentum in both x direction and y direction has to be conserved, right?
So in x coordinate, the conservation law
conservation law is momentum of x. And I mean, the momentum in x direction is conserved because the system has symmetry in space in x direction. Okay.
How about the conservation of mass?
What is the corresponding symmetry? Can you ask it to ChatGPT?
Actually, you can think of it not a conservation of mass, but conservation of energy in a sense. Like being a high energy people say.
But still, can you ask it? Yes.
Hocam, hani şeyi sürtünmesi ortamda topu yukarı attığımızda düşerken attığımız hıza düşecek. O zaman momentum korunmuş olmuyor yani. Ama
No, the direction of the
içinde
yes.
getirdiği için momentum
Yes.
değişiyor.
Yes. The question is, if you throw a ball up, then the momentum constantly changes in y direction. While notice that in x direction, it's always 0. It's conserved. Very good. All right. Let's go back to classical harmonic oscillator. So we have already seen harmonic oscillator, but I didn't say classical harmonic oscillator, right? It was just harmonic oscillator. Now we are putting emphasis on this classical because we are going to get all kinds of problems with it, okay? So how does it look like? It looks like this. Classical harmonic oscillator looks like this. Do you agree? It has an angular frequency k over m, so which corresponds to frequency of 1 over 2 pi square root k over m, because omega is 2 pi f. Did you already know this? Yes? You know. Okay. It has some frequency, it has some angular frequency, etc. Okay. Let's write some of its properties. Classical harmonic oscillator can have any energy. By the way, by energy I mean total energy. So total energy of this system is going to be mv squared over 2 plus kx squared over 2. Do you remember this? Right? So kinetic and potential energy. And if you remember, if you plot it, like let's plot the kinetic energy, let's say it goes like this. Then the potential energy goes like this. And the total energy is constant. So this is the total. This could be kinetic. And this is the potential. Do you remember this stuff? Yes? So it goes back and forth, and it can have any energy. Sounds ridiculous to mention this, but spoiler alert, when you go to quantum mechanics, this is no longer true. Quantum harmonic oscillator wouldn't accept just any energy. Okay? Can I put it this much and release it? It will go like this. I can put it like this much, release it, that much energy. I can just not touch it. How much energy does it have? 0. So let's mention also this pedantic thing, because it will no longer be true in quantum mechanics. Classical harmonic oscillator can have zero energy. Okay? I know that I have mentioned it, but I will repeat it again. The energy, yes.
Is it going to be quantum harmonic oscillator?
No, we haven't reached it yet. I said that it can have zero energy. Classical harmonic oscillator can have zero energy. The energy of classical harmonic oscillator has nothing to do, okay, can be anything, just as I've mentioned before, right? I've mentioned it here. Can have any energy, but I want to stress it one more time. Can have any energy, can be anything. It has nothing to do with its frequency. It's ridiculous to think that it would have anything to do with its frequency. Why? Yes, okay, harmonic oscillator I can have a softer spring which would take longer time, harder spring which would take shorter time, but I can put the same amount of energy to a soft spring or to a hard spring. Doesn't matter. I would just pull this one less, pull this one more, and put the same amount of energy. And any kind of energy can be put in a classical harmonic oscillator.
You mentioned about the principle of stationary action.
Say it again, please. Principle of
Stationary action.
what is it? I don't know that. Okay, sorry. Principle of stationary relations. Stationary action. Are we talking about principle of least action? This one, no, this is just an observation for classical harmonic oscillator. Just an observation. If I put a MSN spring, can I just let it be and it would have zero energy? Yes, it can. Can it have any energy that I put in it? Yes, it can. Okay? But it will change soon. In a few years, in history of physics, it will change. Yes.
When we say classical harmonic oscillator, we mean that a spring and a mass.
Yeah.
That is.
Yeah. That's a classical harmonic oscillator. Or, for example, let's think about atoms as classical beings, which they are not. But if you have two carbon atoms, right? We don't have too much time, so let's linger on this a bit more. So I've already plotted the potential for two carbon atoms, right? And if you release them, they will hang out here, minimum energy, right? But they might oscillate, they might vibrate. Then since they are vibrating, you can think of them as two carbon atoms with a certain mass and with a certain spring coefficient, a system like this, right? And it will just vibrate, right? And if you treat carbon atom classically, right, it can have any energy it wants to have. It will not be the case. It will turn out to be not the case. Okay? Any other questions? Any comments? Okay. So, let me comment myself. You haven't seen, okay, except for action, which I didn't really explain, except for that, you haven't seen anything new. But the point is to mention it one more time, what the classical world means and how obvious it sounds. Like harmonic oscillator can have any energy. It's obvious, and maybe it's a pillar of your thought process, but we are going to break those pillars down when we arrive at quantum mechanics. It will turn out that quantum world is different from classical world, and we have to accept the quantum world because that's deeper truth. Quantum world will be approximated to classical world at relevant time and length scales, but otherwise it's a different world. Okay, take good care.